Oh, I'm there. So, let me see. I have to share screen. I will share the screen that I just had. Let me see where did it go. Let me share the screen. Let's share this one. And I guess I can get started. The first announcement I'd like to make is that I found a larger classroom than this one. So the next lecture, if everything goes according to plan, we will move to the bigger room. The room is Hampton 1113, HAMP 1113. Okay, the same meeting time. It's a nice room because it has a bigger screen than this one. This screen is really puny. You can see things really well from the back, but that room has a bigger screen. Okay. The lectures are going to be recorded on Zoom, and I can share the link with you after the class lecture. I guess I have to switch the camera somewhere, right? So that it points in the right direction. Let me see, where do I switch the camera?
I think you'd have to stop sharing and then switch.
I have to stop sharing. Okay.
And then share.
Okay, let me pause. Stop share. And then change the camera on that one over there, which is this one. And then share screen again. It disappears again. It's not this one. I don't know where it went. Okay, I don't know why this is dark. Well, you didn't get to see yourself. Well, it shows Ivan only. I don't know why it shows. No, I want to share the camera, but apparently it is not sharing the camera.
If you press like one of the ones that has like multiple, like either,
This one?
yeah, that one, and then I think you can see those three little dots in the corner. I don't know why it's black though, but if you want to pin your screen,
This one?
not those ones, but beneath it, if you go down like to where it says, yeah, no,
This one?
You had it.
yeah, like there, and then see those three
this
little
one?
dots, yeah, that one. And then you would say pen,
Pin.
and then you can go back to just one. I don't know why it's black though.
Well, let's not figure it out. I don't want to take away valuable time to figure this out. Let me just minimize it so that you don't get to see anybody. Okay. And then let's get started as to not to waste time. So we talked about Gauss divergence theorem in the last lecture. This time we're going to talk about Flux theorem. Let me just revisit Gauss divergence theorem a little bit again. Okay, from the last lecture, we had the definition for Gauss divergence theorem, and essentially we make use of the fact that we make use of the definition that if you have a field, a flux, okay, D is a field, and if you were to take the divergence of this quantity, is defined to be equal to, you can define this divergence on a very tiny box in space. Okay, you can pick a very tiny box in space, and it can be as small as you want to be. And then you perform this flux calculation, which is the surface integral of the flux going through this tiny surface. This thing will have surface ds. Is writing over here, it's not near the edge. Okay. And then over this closed surface, let's call this surface delta S. And if you perform this calculation, it essentially measures all the fluxes that are coming out of that little volume in all 6 different directions, or the 6 phases. Okay, that is the numerator, but this thing will become vanishingly small when the volume that you pick is very small. So you divide by delta V to make it tend to a constant when you shrink the size of the volume. So this definition of the divergence has a physical meaning that you're actually measuring the fluxes that are oozing out from a point in space. Okay, take, for example, if I take a point in space and I do this calculation, I will calculate all the fluxes that are coming out from that little box that encloses that point. If there are actually fluxes that are coming out from that point, the total calculation that you will have will be non-zero. So it's a measure of how much flux is oozing out from a point in space. However, oftentimes you will have field that looks like this. So if you were to draw a little box around the flux and calculate all the fluxes through all the 6 phases, there's no net flux that is oozing out from that point enclosed by the small box. In that case, the divergence is 0. So that is the physical meaning of a divergence. It's a measure of how things ooze out from a point in space. And if you do this, of course, carefully go through all the mathematics as been shown in the lecture notes, this can be simplified to something like this. Okay, so just as you remember the physical meaning, you go through the mathematical detail, you will get this formula. This is done in Cartesian coordinates. In Cartesian coordinates, this formula is very simple. You can also write this formula in spherical coordinates and cylindrical coordinates and any other coordinate system that is curvilinear, but those are too complicated to remember. Just remember this one and what it physically means, okay? And then today we're going to talk about another operator, which is called the cooperator. The cooperator is a definition of rotation of a field. If a field has rotation, it has co. And for instance, if I have a field E, if it has no rotation, it looks something like this. This is just a hypothetical picture. If this field has no rotation, it will look something like this. Okay? And if you to put a paddle wheel, a small paddle wheel, you know what that is? It's something that if you put in water, it will start rotating if the water has net rotation. So if you to put a paddle wheel in this field, because the field is uniform in all directions, the paddle wheel will not rotate. There's as much counter-rotating force as there is a rotating force. Okay. However, if you have a field that is weak on one side and gradually getting stronger, I use the length of the arrow to denote the strength of the field. If now you put the paddle wheel in this field, the paddle wheel would start to rotate. Can you see that? Okay. So the curl is a measure of the rotation of a field, how much rotation there is. So mathematically, we denote this quantity by this. Okay, and So you're going to learn something, which is that this curl of E can also be defined in a microscopic manner by, for instance, putting a square in the presence of the field, and then define this thing to be something that curl of E then is given to be equal to, or curl of E is actually a vector quantity. Curl of E in the direction that's normal to the surface. This is a small surface delta S. And there is a normal that is pointing out of the paper. Can you see that? N is that unit normal that is pointing out of the paper. The rotation of something is always along the axis of rotation. You probably learned this from your undergraduate physics course. The angular momentum, moment of inertia, all those things are vector quantities, but they point in the axis of rotation. So similarly, if you want to measure the amount of rotation the field has in that little square, the amount of rotation is pointing out of the paper in the n hat direction out of the paper. And if you take this to be the definition of curl of E, you can show that this should be equal to E dot dl. So you take this field and measure its torque. It's like performing this line integral, which is like measuring its torque around a small, a small contour that encloses the thing. And you can think of this small contour as delta C, that encloses the surface area delta S. So if you think about doing this calculation, you're actually calculating those torques little by little, and then summing up on a closed loop. The closed loop need not be a square, but we'll make it a square for simplicity. Again, this torque is going to be very small if you make the area of the loop very small, in order to make this quantity non-vanishing, tending to be a constant, you normalize by the cross-sectional area of that loop. So you go through all the algebras that you need. It's done in the lecture notes. I won't repeat the algebra here. You can find that this formula simplifies to a very simple formula in Cartesian coordinates. Let me assume that I do this where n hat is pointing in the z direction. I won't go to the algebra, but let's assume that I'm doing this for the z direction. You can show that after the work is over, you can show that the right-hand side actually becomes, simplifies to something like this. I'm not going to derive it, but it's derived in the lecture note. If you're not convinced by this, go and read the lecture notes and study that. But this is the measure of the torque of the field that is pointing in the z direction, where I assume that z is out of the paper. And then you can do the same experiment for the x and the y direction. Now you assume that n hat is pointing in the x hat direction. Then you'll find that the right-hand side simplifies to something like this. And then you can similarly do the same experiment for this pointing in the y hat direction. And you will have this in Ex minus partial ET. So I don't know if you can see this. You see, in the divergence calculation, if we have a y component in the field, we take the y component and differentiate it with respect to the y direction. But this is different. If it has a y component of the field, to see if this field has any torque, you look for its variation in the x direction. say this is EY, okay, and this is X direction. To see if this field has a torque, you see if this field is changing in the X direction. That's why it's partial X EY. And similarly for this component, if it does have any torque, it has to look something like this. It should be non-zero. And similarly for the other components. So I think this is the gist of the physics that you have to realize as to what the curl operator is. So it's a vector quantity. And then you can write down in, you unwrap this. This is in terms of 3 components, and you can write this as is done in many textbooks. Okay. I'm not going to unwrap it for you. You have this formula on the left-hand side that you have obtained by performing the experiment. And then you have unwrapped that, you have the identity that you have learned in an undergraduate course. Okay, that is what the curl is. It's a measure of the rotation of the field. Again, you can do this experiment in spherical coordinates, in cylindrical coordinates, and any curvilinear coordinates. And those formulas will be very, very complicated. Okay. I don't hold you responsible for those formulas. I just hold you responsible for the physical meaning of this formula. Okay, are there any questions regarding this? Actually, I have this written out in full. And if you write this out in full, it would be something like this. Y hat partial ZEX minus partial X EZ, and then plus Z hat partial X EY minus partial Y EX. Okay. And this is just XYZ direction, XY Z, of course, this has to be a right-handed coordinate system. X cross Y is always pointing the Z direction. There's something that you should know. We use the right-handed coordinate system. And then if you have something like, so how do you remember this formula? What happens if it's too difficult for you to remember? Well, there is a way for you to remember this formula in a straightforward fashion. The only thing you need to remember is that this del operator can be written as this operator. Okay, and then if you want to work this out, you can do it the long-handed way, which is that curl of E is equal to X hat partial X plus Y hat partial Y plus Z hat partial Z. And then crossing with this E, if you write it on Cartesian coordinate, would be CX plus YEY plus ECEZ. Okay, what do you do at this stage? Taking the cross product of 2 vectors can be quite daunting for some students. But it need not be daunting if you know the simple way. You can use the distributive law. I think it's called distributive law. You can do it term by term. First, you take the cross product of these 2 terms. Okay, take the first term and cross with that term. You have X hat crossing with X hat. From your knowledge of vector algebra, what is X hat crossing with X hat? No? 0. Very good. 0. Okay, remember that. That is the fundamentals of undergraduate vector algebra. So this term is 0. And then you will take this term and cross with this term. So it'll be X hat crossing with Y hat. You have to apply the right-hand rule of cross products that you have learned as an undergraduate. What is X hat crossing with Y hat? Z hat, very good. Okay, that is the right-hand rule. Okay, so you will have Z hat and then partial x e y. This is coming from that term. And the x hat crossing with z hat. X hat crossing with z hat, you have to think a little bit. It's not straightforward anymore. What is x hat crossing with z hat? Very good. Negative y hat, because it's flipping around. Okay, so you will have this. So you can use this rule. You can do that for the second term. You can do that for the third term. You can work out the cross product very easily without resorting to memorizing some complicated formula. The only thing you have to remember is the left-hand side, which is very simple. And some students like to write down the determinant. When you take cross products of two vectors, you have one row, another row of components, and then the third row of components, and then you take these rows and cross them all over. I got confused by that kind of thing. Okay, it's better to remember it this way. Okay, any questions on cross products? So again, on this cross product and the curl of thing, you're going to realize that curl of E is a measure of rotation. And then what you have then is that if you have something like curl of E, and you need to calculate this rotation over a certain surface, ds. And that surface S is something like this. And how would you do this? Well, you do this by, one way of doing this is by dividing this surface into a tiny surface. You have this big S, but you can also break into tiny surfaces. And then you can say that this is the sum of all the curls of each of these tiny surfaces. So you can think of this as curl of EI, just as we did for the divergence theorem case. Okay. And then divided by, that would be equal to that. But then you go back to the definition of what the curl of E is. Okay, you go back to the definition of what curl of E is. You go back to this slide and go back to this fundamental definition of curl of E. And you can convert this into a line integral. And that line integral says that this would be sum of the line integral of each of this over, say, CI. So I take a CI and perform this line integral. And if you can imagine you performing this line integral for each of the squares that I have in that surface, can you see that the line integral for the internal edges are all canceling out? So if I perform a line integral like this, for instance, and then I perform the next one over, you can see that the common edge have the line integrals cancel out. So if you put two surface integrals side by side, the common edge cancels out, leaving the boundary terms left over. Okay. And finally, if you do this for everything, and if you were to perform this integral over the whole cross-sectional surface, only the line integral on the edge survive. Okay, the ones on the edge do not have anybody to cancel with, nobody to tangle with, so they survive. But those inside, they annihilate each other. They fight with each other and kill each other, and they all die. So leaving behind only the boundary terms. So what you have then is that you have this very famous theorem which says that this integral is finally just the integral over the larger contour C. So if this is a big contour C, if you take the curl of the field and integrate over a cross-sectional area, only the boundary term survives and becomes a contour integral on the boundary. This is Stokes' theorem. Okay, this is known as Stokes' theorem. And it's stated here as well. Okay, if you take any surface S, divide it into tiny, tiny surfaces, integrate each surface, applying the definition of what the curl is, you get the right-hand side, which is this Stokes' theorem. Okay. But then there's a catch here. We have only proved this as has been done in the lecture for flat surfaces. How do you know this is good for curved surfaces as well? Well, you can do a very simple geometrical argument saying that any curved surfaces can be replaced with unions of flat surfaces. That is, the statement is in geometry. Like this is a parabola dish. I have replaced it with unions of triangular surfaces. And you can do that for any shapes. And these surfaces are called simplex. And it turns out that in 2 dimensions, a simplex is a triangle. It is able to tile any flat surface that you have, be it curved or flat. So if I apply Stokes' theorem to each of these flat triangles, I can cumulatively add them up and show that finally I will only have a contour integral around the edge as well. So this proof is also valid for curved surfaces. And simplices are very interesting. In 2 dimensions, a surface has a simplex, which is a triangle. In 1 dimension, if you have a line, the simplex in 1D is a line segment. In other words, given any line, you can break into line segments with arbitrary numerical precision. And giving any surface, you can break into unions of triangles or flat triangles with arbitrary numerical precision. And in 3 dimensions, you have to use what is a tetrahedron. Say if I have a 3D object, I don't know, you might have to do a little bit of thinking that if I break this volume, say if this is a volume thing, okay, into sums of tetrahedrons, it can be used to tile any 3D volume. So a simplex for 3 dimensions is a tetrahedron. A simplex for 2 dimensions is a triangle. A simplex for 1 dimension is a line segment. So something about geometry that you should know. Okay. So we have all these nice things, and what can we do with them? We have Stokes' theorem, we have Gauss divergence theorem. We can apply these 2 theorems to simplify Maxwell's equations. Okay. For instance, if we have Faraday's law says that E dot dl over contour C is minus d dt. The time rate of change of the flux linkage, B dot ds. Okay. And then I can use Stokes' theorem, replace the contour integral I have on the left-hand side is a contour integral C over a closed contour. And I can write the left-hand side as being equal to curl of E dot ds. Okay. Where S is here and ds is some small volume that I have over there. dl is something on the contour. So the left-hand side can be written as such. And then the right-hand side, I can also put the total derivative inside the integrand. it will become a partial derivative because B is usually a function of position and time. So if you were to write the right-hand side with the derivative operator inside the integrand, it has to be a partial derivative because B is a function of more than one variable. Now you go about thinking and making the surface as small as you want. When you make the surface as small as you want, you can think of this as being a relationship at a point in space. And then you have Faraday's law written in differential operator form. Okay, this is Faraday's law. Okay, and then you can do the same thing to the other Maxwell's equations, which is Ampere's law. You will get the differential form of Ampere's law. Using Flux theorem, we will have this in partial T d of RT plus J of RT. This is Ampere's law. Let me call it A law. Okay. And then we have the other two that involve divergence. And we already have proven Gauss divergence theorem. And you can write them in differential operator form. It will look something like this. Yes. So now we have all the four Maxwell's equations written as partial derivatives and differential derivatives. And that is beautiful. Of course, beauty is in the eye of the beholder. Okay. So, but to me, it's beautiful. It's such a succinct way to write four Maxwell's equations. And this is a point-wise relationship. It relates the field at this point in space in this manner. No more integrals, no more ugly integrals that you have. And if you're a mathematician, you convert these equations into partial differential equations. And this host of knowledge on how to solve partial differential equations. Okay. So, but Maxwell's equations, we was first derived was not like this. Okay, it was not like this. It was actually Oliver Heavyside who rewrote this equation into this form. Many would call him an eccentric English genius. Okay, and he was a very strange guy. He liked to ride bicycles, and he does not clamor for fame. And in fact, there was another very famous guy who came to visit England and wanted to see him. He didn't want to see him back. Okay, so he was an eccentric person, but he was the one who actually wrote Maxwell's equations in the present form that we are using in textbooks now. Okay. So one thing I want to point to you is that all these four Maxwell's equations are not independent of each other. If you look at four of them that I had in the previous slide on the left-hand side, it turns out that the bottom two Maxwell's equations are derivable from the first two. Okay, these two are derivable from the first two. How can I show you that? Which means that you only need to solve two or four Maxwell's equations most of the time. Not always, but most of the time. You can get by solving the top two because the bottom two are derivable. And how can I show you that the bottom two are derivable? For instance, if I were to take the divergence of a curve, and this has to be zero. Okay, it is probably not obvious to you that it should be zero. But something is obvious to you that it should be 0 if you have had a course in undergraduate vector algebra. This should be 0, shouldn't it? You take B crossing with any vector A, the resultant vector is always orthogonal to B. And if you dot with B again, it always gives you 0. You can prove this by algebra. Okay, you can think in your head, but you can also prove by algebra. Write everything out in Cartesian coordinates. And if you use the same algebra that you use to prove this, you'll find that you can use the same algebra to prove that as well. That is, if you write everything out in gory detail, write the del operator in Cartesian coordinates, and you keep all the terms, they call it dotting the i's and crossing the t's, and then you find that it is also true when you use the del operator. So when I have Maxwell's equations, I can take the, say, the divergence of this equation. If I take the divergence of this equation, then the left-hand side equals 0. Can you see that? Divergence I curl of E is minus dv dt. The left-hand side is equal to 0 for the above reason. So I would have divergence is not time dependent. So I can take the divergence inside and show that this is true. Okay, can you see how I get the second equation? I just take the divergence operator and put it beyond the partial t. Since divergence is an operator independent of time. And then if this is true, then it means the divergence of B, constant of time. Divergence of B is independent of time. Okay, so it may be some constant, but we have never found what that constant is, because if that constant exists, it has the physical meaning of magnetic charges. Since we never found magnetic charges in this universe, we set the constant to 0. Okay, we set the constant to 0, and hence we arrive at the fact that Gauss' law is true. Okay, similarly, you can do the same thing to the second equation. You can take the divergence of Ampere's law. You will get this equation plus J. Okay, and then again, the left-hand side is equal to 0 by virtue of that identity that I just convinced you of, or maybe you're not convinced of. You go back and do the long form and convince you that it is true. And then if I take the divergence of Ampere's law, I have this thing. Okay, but I know that there is something called a current continuity equation that maybe you should know by now, which is that divergence of J is minus partial rho partial T. This is called current continuity equation. Okay, and this equation says that if you have a current flowing, and if you study its divergence at any given point in space, it is equal to the negative time rate of change of the charge density at that point. Does that make physical sense? Divergence of J, as we said before, is a measure of how much current is oozing out from a given point in space. Okay, if there's a net flow of current oozing out from a given point in space, the charge density there must decrease. And if the charge density there must decrease, partial rho, or partial rho partial T is negative, and then the right-hand side would be positive. So if something is oozing out from a point in space, it is positive number, and this would also be a positive number. And this is just a statement of charge conservation. So if we put this in there, then we would have this being equal to 0, and then this would say that one way for this to be true is that plus a constant. Okay, you can integrate this equation and come up with that. But that constant is some constant that is left there from t equals to minus infinity. That was left there to you by your great-great-great-grandfather. You never saw it, you haven't found anything, so you just set it to 0 for simplicity. Okay, so if you set the constant to 0, then we have divergence of t equals rho, which is just Gauss law for charges. So what I'm showing here is that the third and the fourth Maxwell's equations are derivable from the first two. So most of the time, we don't have to worry about the third and the fourth, except for one occasion. Does anybody know the occasion that we have to worry about all four Maxwell's equations? When is the third and the fourth equations not derivable from the first two? Anybody? Nobody wants it. It is the case for statics, electrostatics and inertostatics. If partial t is equal to 0, if partial t had been 0 in these two equations, then these two equations are not derivable from the top two. Can you see that? So for electrostatics and magnetostatics, we have to consider all four. But for dynamic problems, you consider only the first two, and it should be sufficient. So we now have four Maxwell's equations. We know what to do with them. We know how important they are, and that and so we are ready to solve them. Okay, let's go and solve them. But so I'm going to talk about this topic later on. I'm not going to belabor point because they're just taken out of the textbook. But what I have is that I have four Maxwell's equations, which I'm going to write over and over and again until you get bored with them. But I'm sure you won't get bored with them. They're so interesting. So much of our life depends on them. Okay, these are the four Maxwell's equations again. And we say that if partial t is not equal to 0, the first two equations are sufficient. The third and the fourth are redundant. But if you look at the first two equations, it has how many unknowns there? Usually you're given the sources in the problem. J is the input. In solving a system like this, you say J is the input. And then the unknowns are E, H, B, and B. Okay? There are four vector unknowns. Each of these unknowns has three components, so they're all 12 scalar unknowns. But I have only two equations, two vector equations, which means that there are 6 scalar equations, right? If you convert them into scalar quantities. So 6 scalar equations with 12 scalar unknowns, and then I have 2 vector equations with 4 vector unknowns. So the number of equations does not allow me to solve for all the unknowns. So I need more equations. What equations do I need in addition to the first two that I have written down? Does anybody know? Yes?
Constitutive relationship.
Very good. Constitutive relationship. Okay. So in addition to the first two of Maxwell's equations, in order to solve them, we need the constitutive relationship, which is that like in vacuum, writing, so I don't know why. In vacuum, B is mu naught H. D might be some epsilon times E. Okay, so epsilon naught times E, say. Then we have two additional equations to the two that we already had. Then we will have four equations and four unknowns, and we can solve them. So constitutive relations are needed in order to solve Maxwell's equations. Okay, and these are known as constitutive. It's becoming very fat. I don't know. Can I make it thinner? Maybe this will make it thinner. Okay, so the constitutive relationships are needed in addition to the first two. And many of us can remember what epsilon naught is. 8.854 times 10 to the minus 12 farads per meter. And then mu naught is equal to 4 pi times 10 to the minus 7 Henry per meter. So mu naught can be stipulated exactly. Epsilon has to be measured. You will later learn that there's only one constant that can be measured in Maxwell's equation in free space, which is the velocity of the wave. Okay, and that is the only constant that you can determine from experiment. So given epsilon naught and mu naught, you can set mu naught to be an arbitrary constant, and for simplicity, it has been set to 4 pi times 10 to the minus 7. You'll understand this fact in a little while, but you can read the lecture note if I don't have time to discuss it. So electric fields have a unit of volts per meter. Okay, electric flux. Okay, on the other hand, has a unit of coulombs per meter squared. So these are also called flux density because they have units of coulombs per meter squared. And then magnetic field, H, has a unit of amperes per meter. And then magnetic field, B, has a unit of Weber per meter squared. So this is also called magnetic flux density. And this is actually equal to Tesla. Some people would use the term Tesla to replace Weber per meter squared. So if you talk to the medical field people, like the magnetic resonance imaging people, they will always talk in terms of Tesla. How big is your MRI machine? 7 Tesla, then you will feel very proud. 10 Tesla, you will feel even better. In the beginning, it was only 3 Tesla. And I think the Earth magnetic field is very weak. I forgot how weak it is now. Okay. So let's go to material medium and more on material medium. So we have the constitutive relationship for vacuum, which is very simple, but for material medium, and let's assume that we have linear medium, then the constitutive relationship becomes slightly more complicated. In addition to the vacuum term, you will have to add a polarization density. Okay, this is called polarization density. And this describes material properties. What it says is that if I have a material is usually made of molecules, or atoms or something. So if you have material medium, if you apply an electric field, the medium is going to have molecules inside that makes very small dipoles. And this dipole is going to follow the direction of the electric field. You can have many of them pointing in different directions. And these dipoles usually are pointing in random direction, but if you apply an electric field, then it starts to be pointing in the direction of the electric field. Okay. So these little dipoles give rise to dipole densities. You can calculate these dipoles in terms of how many dipoles you have per unit volume. And then you can write down a polarization density. It says that the total electric flux is a contribution from vacuum plus that from the polarization density. Okay, you will understand why it is additive, because you will understand that later on. So you can think of the polarization density P has been epsilon naught chi E for linear medium. If the medium is linear, the polarization density is just linearly proportional to the applied field. And if that is the case, then you can write this polarization density in a fashion that is and then you can write this as 1 plus chi E. And you can think of this as epsilon E, but this is an effective epsilon. So if you have polarization density, how the constitutive relationship changes is that you replace the vacuum permittivity. This term is usually called the permittivity. Okay, this term is usually called the permittivity, and this term is called the permeability. You replace the vacuum permittivity with this other one if you have a polarization medium. And what happens is that if you have a polarization medium, it gives rise to what is called the displacement current, because you know that Maxwell's equation says that curl of H is partial V, partial T. And this, as we say, is displacement current. And this actually consists of two terms. It will consist of the free space term plus a term from the polarization density plus J. So this is also current flow. Let me see. What is it? So this term is from little dipoles, or from dipole density. So you can think of these little dipoles that they line up in molecules in the material medium, and that they allow a kind of current to flow through them, and that current is called the displacement current. It is very much akin to the fact that if I have a whole bunch of capacitor, no current can flow in the DC limit. But if I connect this to a AC current, and if the AC current or AC source, voltage source is changing with time, it can drive a current to this system. So the polarization density gives rise to displacement current in space. Even when the space is an insulator, a kind of current can flow through that space. And that current is called a displacement current. Okay. And then that is from the second term there. And you can think of flow of displacement current in space very much akin to how electric current flow to a series of capacitors, each of which is an open circuit and insulator. Okay. So if you have a permittivity medium that is not a vacuum, you have additional displacement current flow. Okay. This term, which is the polarization density, give rise to addition displacement current, and usually things are not that simple. Things are not that simple, and that even though we have, say, D is epsilon E, and the problem is that this relationship is not that simple because it has to do with the fact that you're trying to polarize the dipoles in the medium with an electric field. And that polarization cannot be time independent, which means that to be strictly correct, this should be a transfer function. So this is the most general way to write down a linear system theory. If something is linear, then the D and the E should be related by a transfer function or a convolution. Okay, it should be a convolution, and that should be the general relationship, which means that if you were to write this in the frequency domain, something that you will learn later on, time domain and frequency domain, then is a constant in this manner. Okay. So when we have something like this, for instance, D is epsilon of E, we always also write this with respect to vacuum and write it in this manner, and this is called the relative permittivity. And similarly, if we have a magnetic flux, you can also do likewise. It refuses to erase, and I know that one way to do that is from here, but I don't know why. So if I have B, which is equal to mu H, and similarly, you can also write this as mu naught mu R H. And this will be called a relative permeability. Okay. So let's look at the vacuum case where things are constant, are truly constant. Mu R is 1, epsilon R is 1. Then in vacuum, then we have this very simple relationship. B is mu naught H, and mu naught and epsilon naught are truly constant. They are even constants independent of frequencies. That is something very difficult to find in true material medium. So if I were to start with Maxwell's equations, then I say that curl of E is minus dB dt. And then this can be written as mu naught dH dt. Again, it refuses to be erased. Maybe I have another pen. Okay, this time erase always confuses me as to why sometimes it can erase and sometimes it cannot. I have to hold 2 pens, one for erasing and one for something. Okay, then it works. Very strange. So if we have Maxwell's equations in vacuum, this is what we should have. And then the other equation is this one over here, which is the d dt plus j. And let's assume that we're in vacuum, so there's no current flowing. So this will be just that. And then this will be epsilon naught d dt of E. Okay. And then I'm going to show you that these two equations are very important in the sense that you can show wave phenomenon coming out from these two equations alone. And let's see how we can do that. So you take the curl of the first equation. Say if we call this 1, if we call this 2, and if I take the curl of 1, okay, and then the left-hand side will be curl of E. And then the right-hand side will be minus mu naught partial T curl of H. As I said before, curl is something independent of time, so I can swap space derivative and time derivatives quite easily. So the first of Maxwell's equations becomes that, and then you know what curl of E is. I mean, you know what curl of H is. You get it from the second Maxwell's equation. So you plug that in, then you get minus mu naught epsilon naught partial square T square E. Can you see that? The right-hand side, if I take the second Maxwell's equation and substitute for curl of H, right-hand side just becomes second derivative in time. Can you see that? Okay, I see some nodding heads, which means that it is not confusing to everybody, which is wonderful. So you're still following me. So what is so special about this equation? Well, this is sometimes called the vector wave equation. And it can be simplified further if you know how to simplify the curl of E. What is this equal to? Again, you use vector algebra to simplify this. There's something that you should remember in this course. A cross B cross C is B A dot C minus C A dot B. Okay. This is a vector algebraic equation that you should commit to memory because it is very useful. You will use it over and over again. So let's just do some sanity check to see why this equation makes sense. Okay. I'm not used to talking with the mask on. So this equation, okay, it's called the back of the cat formula, and it's something that you should commit to memory. And let's do some sanity check before we derive. We don't have to derive it, we just have to memorize it. But let's do some sanity check. So if you have three vectors, A, B, and C, if you cross B with C, it will be pointing in the third direction that you do not know what it should be. But if we cross this vector with A, will this vector finally be pointing in the A direction? I have three vectors A, B, C. If I cross B with C, would B cross C B? And then I will cross it with A again. Would the final right-hand side be pointing in the A direction? No. No, very good. Okay, no. So you know that there cannot be any A components. So you write the right-hand side as a linear superposition of B and C. Okay. And then you go through quite a bit of algebra. If not going through the algebra, you can read up some clever mathematics book. They show that the two components are linear superposed in this manner. Okay, so it makes sense. Okay, that's sanity check. But there's another way to remember this formula really well. It is called back of the cat formula. If A cross B cross C, the right hand side is sitting at the back of the cat. Okay, and if you know how to put the dots and the parentheses correctly, it's called the back of the cat formula. Okay, just memorize this formula. Then if I apply this formula to this one, okay, call each of this A and so on. So you can see that this will be just equal to that. You have to be careful when you derive something that is for a scalar number or constant number, and then later on use that equation for a differential operator. You have to make sure that your differential operator is always acting on something, and that something that you're acting on has to be to the right of the differential operator. So when I apply the back of the cat formula, I deliberately put this vector to the right. Okay, the A dot B is replaced by del dot del, which is a scalar. It has to operate on something. So I put the E, which is C in this equation, to the right-hand side. And you can also prove the back of the cat formula by long-handed algebra. And you can use the long-handed algebra to prove the first line too. Or you can just remember the back of the cat formula and make it same so that your differential operator is operating on something to its right. Okay, don't write nonsense down. If the differential operator has nothing to operate on, the equation is wrong. Okay, so, but we are talking about vacuum in this case. Vacuum in this case, what is divergence of E in vacuum? We follow Maxwell's equations, remember? The third and the fourth one was this. But in vacuum, D is epsilon naught E. Okay, and there's no charge in vacuum, agree? No charge in vacuum, so divergence of D equal to 0. Okay, but B is epsilon naught E, this implies divergence of E equal to 0. Can you see that? So in vacuum, the electric field is divergence free, is how people say it. There's no divergence, so divergence free. So I can drop the first term on the right-hand side, and hence write curl cross curl of E is equal to just del dot del of E. And this usually is written as Laplacian of E. This is called the Laplacian operator. And then you can work this out, what the Laplacian should be. You can actually, we already know what the del operator is. Del operator is given to be this. And then the Laplacian will be just equal to del dot del, which is just partial square, partial x squared, plus partial square, partial y squared, plus partial square, partial z squared. And then now if you were to look for a solution of this equation that we have derived, okay? We have derived this equation earlier. I guess I skip a page there. So I derive this equation, but the left-hand side can be replaced with the Laplacian operator because this term can be dropped out. So finally, I have an equation that looks something like this. I don't need to see my bill. Okay, I don't know, it's unintentional. So finally, I end up with an equation that looks something like this. Okay, this is like a wave equation of some sort. But then to make life simpler, I let E be pointing in a certain direction, x hat Ex dt. So I'm assuming that I have x and y, and then I have z. I have a wave that is propagating in the z direction. The electric field is pointing in the x direction. Okay. And the electric field is only changing with respect to z. And if that is the case, you can clearly see that divergence of E equal to 0. Can you see that? Divergence of E equal to 0. Divergence of E pointing in the x direction, divergence of E implies that you have to take partial derivative with respect to x. But E itself is just a function of Z. So it is 0. So it satisfies the divergence precondition that we have implied in deriving this equation. We have assumed that divergence of E is equal to 0, and this choice of a guess solution satisfies that. And then you can show that, well, you can show that Ex actually satisfies this equation now. Okay, and how many of you have seen this equation before? Very good. Many of you have seen it. This is called the, what equation is this? Yes, a wave equation in one dimension. Okay, this equation has been solved by many courses. So you can actually, so I won't, since I'm running out of time. So the solution for this equation, say if I were to plot x as a function of z and t. Okay, it will look something like this. The shape can be arbitrary. Then this wave would move to the right. You can also have solution where the wave moves to the left. Okay, and then you can show that the general solution is actually of the form of a right traveling wave plus a left traveling wave. Okay, and I will let you read about that in the lecture notes. Okay, so about what wave equation is and so on. And actually, I drew the picture here. Okay, the other thing that I like to talk about the remaining time is to talk about Green's function in static Green's function, in a sense that if you have static electromagnetics, okay, partial t equal to 0, then Faraday's law is just equal to that. Ampere's law is just equal to that. And again, as I said before, you have to solve all the 4 equations, because the third and the fourth is not derivable from the first anymore. And then in order to solve this equation, you let E be equal to the gradient of something with a minus sign in front, so that this equation is automatically satisfied. Because you can easily prove that curl of gradient of something is always equal to 0. So the first equation is always satisfied. And by so doing, you have to solve the third and the fourth equations as well. And if I assume the vacuum case, then D will be just epsilon E gradient phi is equal to rho. Okay, if I plug this into the third equation, I get this equation. And let's assume that epsilon naught is a constant, so I can take it outside. Then I will have this equation. And this equation is called Poisson's equation. Okay, Poisson's equation, which has been solved by many people over again. but we know the solution of Poisson's equation for a point charge. That is according to Coulomb's law. Okay, so if we have a point charge, so what we know is that the E, according to the work of Coulomb, looks something like this. Okay, this is a finding of Coulomb's in the 1700s. But then in electrostatic, we know that the electric field is the gradient of phi. Okay, you can put one and one together and actually figure out that the phi that can give you this correct answer is something that looks something like this. So which means that you know from Coulomb's work that the potential due to a point charge looks something like that, which means that if I Poisson's equation, which is written for the general charge on the right-hand side, and if the right-hand side is a point charge, I can replace that with the delta function. Okay, which means that you know that the potential due to a point charge is already known from Coulomb's work, which is the first and the second line. So I know the solution to the third equation right away by drawing upon or standing on the shoulders of the giants before us. Okay, so I know the solution of the third equation, and it must look very much like this, but written in the coordinate independent fashion. So I would say that Q would be equal to 4 pi epsilon naught r minus r prime. Okay, so in fact, we know how to find the solution to Poisson's equation when we have a point source on the right-hand side. And that's what electrical engineers are very good about. That is, if you know how to find the solution to a problem due to a point source, you can find the solution due to a general source by using convolution. Okay, in this case, 3D convolution, because you learned that from the linear system theory. If you know how to find the impulse response of a system, you know how to find the general response of the system. So if you know the point source response of this system, you know how to find the general response. Okay, I'll stop here because I'm running out of time.